Hey guys, this video is going to be about calorimetry. So calorimetry is basically the act of measuring a change that's going to be able to demonstrate a transfer of heat between two systems. And to do calorimetry, we use calorimeters. And so the way you can remember that, heat is a source of energy and calorie is a source of energy for us. All right, so in order to be able to measure a change in heat, we have to know the specific heat of a substance. And so the specific heat, or the specific heat capacity, is the amount of heat required to raise the temperature of 1 gram of a substance 1 degree Celsius. So the best way that I can explain specific heat is, imagine that you're at the water park and you're not wearing shoes, right? And you're walking on the hot concrete because you wanted to get a snow cone, and your feet are burning and you're trying to find that blue padded stuff that they put on the concrete so that you can step on it because it's much cooler than the concrete is itself. Well, that's because the concrete has a much lower heat capacity, so it takes less heat to heat it up, and so it gets hotter in the hot sun, right? So if you look over here, remember I said heat is the amount of heat, so heat is measured in joules, required to raise the temperature of 1 gram of something 1 degree Celsius. Okay, or we can measure it in Kelvin. The value wouldn't change. I know that's hard to believe, but the value wouldn't change because this is a change in temperature. It's not a temperature. So it takes about 4.18 joules per gram, every gram of water, to heat up 1 degree Celsius. And solid or ice, it takes about 2.03 joules of heat. Aluminum is much lower, iron is even lower, and then solid carbon is 0.71. So those are just some various values. So you can see they vary a whole lot. So if we had all of these substances and we wanted to know, so let's say we have 50 grams of each of these, and we applied the same amount of heat to them, which one is going to be the hottest? Well, it's going to be iron, because it takes less heat to heat it up. So if we apply the same amount of heat to all of them, then its temperature is going to raise much higher. All right, and that's why your seatbelt buckles in your car are so much hotter than everything else in there, because they're made of metal. So when they touch you after sitting in the hot Texas sun all day long, they tend to burn. So the math of specific heat. So specific heat, you can use this formula. I generally never used it really all that much, but I'll use it because it's on your formula chart. I just use the units because the units of specific heat tell me what I need to do. Where Q is heat and M is the mass. The C is specific heat capacity. I've also seen it used as an S. And then delta T is the change in temperature. And remember, change, delta, is final minus initial. All right, and so just if you're curious, 1 calorie is equal to 4.18 joules. So it actually takes 1 calorie of heat to raise the temperature of water, raise the temperature of 1 gram of water 1 degree Celsius. So the heat capacity in calories for water is 1 calorie per gram degree Celsius. So you can use either one of those. And if I rearrange this equation for specific heat, then that means I would be dividing both sides by, let me write it over here. If I wanted to solve for specific heat, I would divide both sides by M and delta T. Mass and temperature cancel out. And so remember that heat is measured in joules, mass, grams, and change in temperature would be degrees Celsius. So there's my units for specific heat. So that's why I said I always just tend to use the units, but you can use the formula. It's on your formula chart. All right, so the calorimeter is what we use to perform calorimetry, and it's a device used to measure the exchange of heat. We will only look at constant pressure calorimetry. We don't need to look at constant volume. So constant pressure means that it's open to the surroundings and gas that may be produced by the reaction can escape. So it's not, the pressure inside of the container is not changing. And so remember, sometimes they'll ask for delta H, sometimes they might ask for heat, but in this case, it's always going to be the same thing because at constant pressure, heat is equal to delta H. Okay, so a constant pressure calorimeter is usually a couple coffee cups. So they stick a couple of insulated cups together so that it's well insulated, and some sort of styrofoam lid or a cork lid or something. And then sometimes you'll have a little stirrer in there that you can kind of wiggle it around a little bit or go up and down with it, and it'll stir the solution up. The reaction mixture would be inside of the cup, and then a thermometer is placed in there to measure the change in the temperature. So the reaction takes place inside of the cup so that the heat is not exchanged with the outside world. So hopefully this right here is insulated well enough to where heat can't escape and get out. It's not 100%, but it works pretty good. And then the change in the temperature of the water can be measured. So one thing that has to be kept in mind here is if you put a reaction in this container inside of the water, then the water is absorbing the heat from the reaction. And so that means that the heat is released from the reaction, so you have to change the sign, and it's absorbed by the water. So always remember that the heat absorbed is equal to the heat being released, but the sign must change. All right, how much heat would be needed to heat 250 milliliter sample of water from room temperature to boiling? So these are some simple calculations, just using the specific heat so that you can see how it works. So it says that the density of water is 1 gram per milliliter. Hopefully you know that. If you don't, that's something you might want to keep in mind. It's something that you need to assume at all times on the AP test, even if it's not given to you. So if I have 250 milliliters of water, then I have 1 gram per every milliliter, which means I'll have 250 grams of water. And I have an initial temperature equal to 25 degrees Celsius and a final temperature of 100 degrees Celsius because I'm heating it to boiling. So my delta T is going to be 100 degrees Celsius minus 25, always final minus initial, and that's equal to 75 degrees Celsius. So right now I have this and I have this, and I also know that my specific heat for water is equal to 4.18 joules per gram degrees Celsius. So my formula for this is heat is equal to mass times the specific heat times the delta T. So I will plug those values in. That's why I calculated mass to begin with. And I've got 250 grams of water. And there's 4.18 joules needed for every gram to go up 1 degree Celsius, and we want to go up 75 degrees Celsius. So my degrees Celsius cancels out, my grams cancel out, and I end up with joules. And I get 78,375 joules, or 78.4 kilojoules. And to go from joules to kilojoules, there's 1,000 joules in 1 kilojoule. You just divide by 1,000 if you set up the dimensional analysis, or not, just do it in your head. Okay, so the next question, it takes 585 joules of energy to raise the temperature of 125.6 grams of mercury from 20 to 53.5 degrees Celsius. So this is my initial temperature and this is my final temperature. So to change the temperature, I'm going to have to go up 33.5 degrees. Okay, so my formula, Q is equal to mass times C times delta T. So I'm going to plug those in. 585 joules is equal to 125.6 grams. I'm looking for my specific heat, and my delta T is 33.5 degrees Celsius. So I'll divide both sides by 125.6 grams and also by 33.5 degrees Celsius. So my C ends up being 0.142 joules per gram degrees Celsius. Now this says molar heat capacity, and I haven't really talked about that. I just kind of put it in here because it's really not hard and makes you pay attention to the units a little bit. So molar heat capacity has moles instead of grams. So I need to change this grams to moles. So I'm going to take 0.142 joules per gram degree Celsius, and this is of mercury. So mercury's atomic mass is 200.5 grams per mole. So that means 1 mole has a mass of 200.5 grams. So if I multiply by 200.5 grams per mole, grams cancels out and I'm left with moles instead of grams. And that gives me 28.5 joules per mole degree Celsius. All right, so this one's a little more complicated, so we're going to read and write out everything. Okay, so it says that we have 1 liter of a 1.50 molar barium nitrate solution, and we also have a 1 liter 1.50 molar sodium sulfate solution. And both of them are at 25 degrees, so the initial temperature is going to be 25 degrees Celsius. And we get a white solid precipitate, and the temperature of the mixture increases, so the final temperature is going to be 28.1 degrees Celsius. So that means, really quick, I can already tell that my change in temperature is going to be 3.1 degrees Celsius. I'm going to go ahead and mark that so I can find it easier. Okay, and it says, assuming that the calorimeter absorbs a negligible amount of heat, the specific heat capacity of the solution is 4.18. So I've got C is equal to 4.18 joules per gram degree Celsius, and that my density is 1 gram per milliliter. We want to calculate the enthalpy change per gram. So I want the joules or kilojoules per gram of barium sulfate. And then I also want the kilojoules per mole of barium sulfate. And then we're given the reaction. Okay, so I'm going to find this one first because it'll be a little bit easier. What I have to get that is I need heat and I need the moles of barium sulfate. So heat would be a little bit easier, I think, to calculate first. So I'm going to start there. First, I know that all I'm putting in the solution is 1 liter of barium nitrate and 1 liter of sodium sulfate, so that would make a 2 liter solution. So that means that I have 2 liters, and I'm giving a density of 1 gram per milliliter, so I'm going to convert this to milliliters. So 1 liter of solution is 1,000 milliliters, and then there is 1 gram per every single milliliter, so that means I have 2,000 grams. So that's my mass, right? And then to find heat, heat is going to be Q is equal to mass times C times delta T. So I have my delta T, I have my specific heat, and I have my mass, so I'm just going to plug those in. So my Celsius cancels, my grams cancel. What I end up getting for Q is 25,916 joules of heat. So I have my Q right here. That one's done. So now I just need to find moles of barium sulfate. All right, I know that I need this, but I don't know how much of that I have. All I know is I've got this and I've got this, which means I have to do a mole-to-mole ratio to go from one substance to another substance. So I'm going to start with barium nitrate. I have 1 liter of barium nitrate solution, and there's 1.50 moles of barium nitrate in every single liter of barium nitrate because that's the molarity. And then I know that there will be 1 mole of barium nitrate for every 1 mole of barium sulfate. I'm going to move this heat. Okay, and since I have another reagent, this could be a limiting reagent problem Now I see that they're both going to be the same thing, but in case you don't, I'll go ahead and do the other calculation. So I have 1 liter of sodium sulfate solution, and every single liter of sodium sulfate, there is 1.50 moles of sodium sulfate. And for 1 mole of sodium sulfate, I get 1 mole of barium sulfate. So that means here I'm going to get 1.50 moles of barium sulfate, and here I'm going to get 1.50 moles of barium sulfate. All right, so moles of sodium sulfate cancel with moles of sodium sulfate, liters with liters, liters of barium nitrate, moles of barium nitrate, moles of barium. So that's how I got these values. All right, now I know that when we get 1.5 moles of barium sulfate formed from these two solutions, then that means that I am completely out of this and I'm completely out of this, because that's all either of them can make. So neither one of them is a limiting reagent. We don't really have one here because they both create the same amount. And it's going to be 1.50 moles of barium sulfate. We can't make more than that because that's all that can make. So don't add them together. All right, so then to find kilojoules per mole, I'm just going to take this value and divide by 1,000, because there's 1,000 joules in 1 kilojoule, and that's going to give me 25.916 kilojoules, and I'm going to divide that by 1.50 moles of barium sulfate so that I get kilojoules per mole. That's what I want. What I end up finding is that I get 17.2 kilojoules per mole of barium sulfate. Now, here's the tricky part, guys. All right, this heat really, and I could have done it all the way up here, but this heat was what the solution absorbed, why the temperature went up, which means when the barium sulfate was formed, it released that heat into the surroundings of the solution so that the thermometer could read it. Okay, so that has to mean that these are all negative heats because it was released to the solution. That's why the temperature of the solution went up. All right, we can't put our thermometer right on the atoms. We can only feel what happens to the surroundings of the reaction. It's the same thing when an explosion goes off. That explosion is releasing heat. It is exothermic. That's why we feel the heat. So it would have a negative value for the chemical reaction. All right, so here's this, and then I know I also want it in kilojoules per gram. So barium sulfate, barium has a mass of 137.33, sulfur is 32.07, and oxygen is 16, and there's 4 of them, which means my molar mass is 233.4. So I'm going to take my negative 17.2 kilojoules per mole of barium sulfate, and I'm going to say, okay, 1 mole of barium sulfate is 233.4 grams. That allows me to cancel out moles of barium sulfate and get kilojoules per gram of barium sulfate. And the value is negative 0.074 kilojoules will be released. 0.074 kilojoules of heat will be released every time 1 gram of barium sulfate is produced.